midterms. Please.
It's like a quantum system. If I grade it, if I don't grade it, you have hope.
Yeah.
Right? Why do you want to get rid of hope?
I just have anxiety.
I'll grade it. I'll grade it before. Well, I'll grade it in a few days. I won't make any before Thanksgiving. How about that? Okay. Yes, exactly. So we are now going to talk about mixtures. Specifically, we will talk a little bit about mixtures of phases, and then we will spend a lot of time talking about mixtures of different components. So you all are chemistry majors, biophysics majors, chemical physics majors. Why should a chemistry student care about things? There are three terms here, right? There is mixtures, there is phases, there is components. So why should a chemistry student care about any of these? Chemistry is the science of mixing, if you think about it, right? Chemistry is mixing, period. That's one way of defining chemistry, right? You mix things together and see what happens, right? And when you mix things together, they will have different components, right? You will have different chemicals. Component is a way of thinking about different chemicals, right? Independent things that you can vary. And phases in chemistry, well, is it solid? Is it liquid? What type of solid it is, right? So it's fundamentally important to chemistry students. And for a similar reason, it's important to chemical physics students, right? Same type of arguments. How about biophysics students or biology students? Why should a student of biology care about phases? Elizabeth, you're a biologist, right? You tell me, why should a biology student care about phases? Yeah, and they will never end up in our human body. Do we have only liquids? No, we also have solids existing. And in fact, if you think about the boundary of a cell, what is the boundary of a cell? Is it a Donald Trump style wall? No, not quite. It's actually phase separation. You have two liquids and there is just a difference of density. So phases matter a lot for biology also. And right, and biology, I mean, there cannot be a better example of mixtures than biology, right? We have so many things existing. Think about the crowded environment of a cell. So these things are very important. And I say this because whenever I try to give you big picture overview, it means a lot of algebra is going to follow, okay? So you don't lose sight that why are we doing all this algebra. So we will spend a lot of time talking about mixture of components. Before that, I want to talk about mixtures of phases. What do I mean by that? So let's think about our phase diagram of water, which approximately looked something like there was a negative. This is pressure temperature phase diagram. And I'm being sloppy with the other slopes, but the main thing to remember is that where is the solid here? This one, right? And this is liquid, and this is vapor. And for water, the main thing to remember is that this black curve faces negative slope, right? It has a negative slope. For everything else, it will have a positive slope. So this point over here was the critical point, right? Sorry, the triple point. At the triple point, we could have three phases existing together. That was one example of mixture of phases, right? Along the boundary, we had liquid plus vapor existing together. And in this region, you have a single phase region. You don't have a mixture of phases. In this region, you have a single phase region, but along the boundary, you have a double phase region, right? You have a mixture of phases. And over here, you have solid plus vapor. And over here, you have liquid plus solid. This over here is a very, very special point that at least the chemistry students have probably, I hope, have seen it in their undergrad. Does anyone know what's the name of this one? Critical point. So it's characterized by a particular pressure PC and particular temperature TC. And this liquid vapor boundary stops there. Critical point, beyond the critical point, there is no liquid vapor boundary. It's a very, very special point at which the critical point characterizes the point at which liquid starts to behave like vapor and vapor starts to behave like liquid. And you can go and look up lots of video on this. And liquid, the critical point exists not just in water, but in everything. So it is the point at which surface tension between liquid and vapor disappear. So what do I mean by that? Let's think about this liquid vapor phase boundary anyway, and let's work at a constant pressure. At this constant pressure, let's increase our temperature. Okay, let's increase our temperature as we go from this point gradually towards this point. That is boiling, right? You have atmospheric pressure or some pressure and you're just increasing temperature. Anytime you boil something, if you're a PhD student, you probably eat a lot of pasta, right? It's quickest to eat. That's what I used to cook. I still eat a lot of pasta. So when you boil water for pasta, for rice, or anything else, how does boiling work? You have water, right? And you start heating it. What happens at a certain temperature? Does the whole thing just become vapor? No, what happens? Bubbles start to appear, right? Bubbles of different shapes and sizes, and some bubbles disappear, some bubbles keep growing, right? That's an example of nucleation. We'll study about that at the very end. So until this pressure and temperature, when you go from liquid to vapor, you will see there is liquid and there are bubbles appearing on top of it, right? You can see both of them at the same time. But if you were to try to cook pasta above the critical pressure, that won't happen. Any fluctuation in the liquid will become a whole bubble. And similarly, any big bubble can go back to liquid. It's very funky. There is just no surface tension. It's just the whole thing disappears. So that's what we want to understand, what this really means. And you will get a better understanding of this in StatMech next semester. You will try to look more carefully. Garrick Papayan will be teaching and will show you more carefully about what really is critical point and what does it mean. So let's try to understand how this critical point can happen in a simple model. So for this, I will switch gears a little bit and not think about pressure, temperature, but think about pressure, volume, space. And I would like to draw here isotherms in this space, okay? What's the simplest system we all know of? That's the ideal gas law, right? That's the simplest equation of state you can think of. Ideal gas law, the equation of state, if you drew it, it would look something like this at a constant pressure. It makes sense, right? PV is equal to nRT. So as volume goes to zero, pressure has to become infinite, right? Because their product is some constant temperature. As pressure goes to zero, volume has to become infinite because that pressure is some constant. Will an ideal gas law, can you describe water using the ideal gas law? What's wrong with that? Is water an ideal gas? It's highly complicated, right? You have these 1808-degree pentangles, there is hydrogen bonding and everything. Most importantly, ideal gas law doesn't tell you whether it's liquid, solid, or gas. It's just gas. It's just one phase, right? So ideal gas law does not tell you that different phases can exist. We have to go to an equation of state. So the simplest equation of state, not to be confused with fundamental equation. Remember, you can go from many equations of state to a fundamental equation. You can go from one fundamental equation to all equations of state, right? But if you're missing some equation of state, you might not get the fundamental equation. So simplest equation of state is ideal gas law. This does not permit phases. So we have to, in order to think about phases and all this stuff, we have to think of something slightly more complicated. What is more complicated than an ideal gas law? Van der Waals equation of state, right? So how do we write that? So yeah, I always forget how to write it. So what I do is to think about the ideal gas law and think that, yeah, there is a finite volume of particles. So that I write as V minus NB. And then there is existence of attractive forces, right? And these attractive forces depend on the density of square of the density of particles. So it looks something like this. This is how I remember ideal Van der Waals equation. This one is much more interesting. So the first thing I would like to do today is to plot the Van der Waals equation of state in a PV diagram. how would it look like? At very high temperature, let's start with that one. At very high temperature, how would this curve look like in PV diagram? Any ideas? It will look like the ideal gas law, right? Why? Because if the temperature is very high, which term dominates? This term dominates, right? You're taking T and making it really, really high. The relative contribution goes to 0 as T tends to infinity, okay? So very high temperature, the van der Waals equation of state looks like an ideal gas law, right? Just everything becomes ideal, density, volume becomes so much, yeah, you think of it in many different ways, but this is one way. Now, at finite temperature, however, how will it look like? That's the harder one. Does anyone?
So if we decrease the pressure very low, then it can again act as an ideal gas.
I don't want to do that. So I want to study the variation of, you can do that, but I don't want to do that. I want to study variation of pressure with volume, right? So make the temperature very low, make the temperature smaller, not just very low. Okay, let's not make the temperature go to 0. Let's think about a finite temperature where both of these terms are significant. And I want to plot it in pressure volume space. Any ideas? Go ahead. No, it won't look similar. It will look a bit more complicated. Let's try to rewrite this equation and write it in the following manner. Let's multiply left-hand side with V minus NB and V square. Then this is going to be nRT V square, and this is going to be AN square V minus NB. So temperature is constant, B is constant, N is constant, A is constant, right? And we are thinking about pressure as a function of volume, or volume as a function of pressure. Is this a linear equation? Is it a quadratic equation? It's a cubic equation, right? You have power 3 of V. So how many solutions does a cubic equation have? 3 for construction, right? And I'm missing Shah today because he would have raised his hand and be like, well, what about one is complex? So let's talk about real solutions, right? It will either have one real solution or 3 real solutions. If it's one real solution, then there have to be 2 complex solutions which are conjugate of each other. But in reality, it's likely going to have 3 real solutions in most cases, right? So for any given pressure, if you fix the pressure, you expect to obtain 3 particular volumes for which that pressure can be obtained, okay? This is because this is a cubic equation, cubic in V, okay? That's all I can tell you from staring at the equation. Now, if you actually went and plotted it, you would realize that it will look like follows. It will come down. So here it will look like, and this is what Subhadeep was also pointing out, that at very low pressure, it will, there are ranges. You can see it will have ideal type behavior, but it's in the middle, it will be complicated. It will come down, then it will go up, it will again come down, and then it will keep going down like this. Okay? At low pressure, it will again start to look like an ideal. So this is how it's going to look like. A van der Waals equation of state at some finite pressure. So, okay. At very, very high volume and at very, very low pressure, we expect it to look like an ideal gas, right? So we expect it to behave like a gas, okay? So in this regime, it will start to look like a gas. And I'm going to use the symbol G here instead of V, even though in the phase diagram I was writing vapor because I have V for volume, okay? So here it looks like gas. At very small volume and high pressure, it will look like a liquid. So van der Waals equation of state still does not give you a solid. It kind of gives you liquid and vapor. It does not really allow that much complexity. It's better than ideal gas, okay? So for getting solid and stuff, you will have to go to virial equation and add more corrections to it. So in this part, on the very left, you have a liquid. And in this part, on the very right, you have a gas, okay? And this middle region that corresponds to liquid plus gas coexistence. Okay, and let's try to understand that. So here I drew equation of state for a van der Waals gas, which is better than an ideal gas, right? But it's still not perfect. It's still assuming, it still has a bunch of assumptions, right? So I'm going to go to the next page. I will draw this curve, and then top of it, I will draw a pressure volume curve for a more real system. And I will, yeah, go ahead, Lydia.
So does the Van der Waals equation not also stop at gas? How do we know that it would, how do we get liquid out of that? How do we know that it would be liquid? Based on the Van der
I will give you a sense. I will give you a sense of it in a little bit. Let me just go to the next page. Yeah. So let me draw this thing again. So we had pressure, we had volume. At very high temperature, it looks like this. At a finite temperature, it looks like this. So at any given pressure, you have three particular volumes that can exist, okay? So that's a van der Waals equation of state, and I'm gonna come to your answer in a bit, Lydia, just in a bit. For more realistic materials, the equation of state looks as follows. It tends to follow the van der Waals equation of state till here. Then instead of showing this curve, you get something like this. Let me draw it a bit better in a thicker line. So it will look something like this, okay? So this bizarre dome that you see, or the curvature that you see in van der Waals is an artifact. Real materials don't have it. So I don't want you to think too much about van der Waals. I want you to think about the so let me label things here. So this is at very high temperature, van der Waals tends to look like ideal. At some finite temperature, you have van der Waals that exist like this. But what I just said is that experimental measurements show that real chemicals, real materials tend to look something like the black curve. So so Lydia asked, how do I know that on the right it's gas and on the left it's liquid, okay? So my question back to you, Lydia, is what is the difference between a liquid and a gas? Solid is kind of easy, right? If you kick it, it will probably hurt. That's one way of thinking about a solid, right? Liquid and a gas are a bit harder to distinguish, right? It's kind of the same if you think about it. Liquid tends to preserve, when you do StatMech next semester, you will see these pair correlation functions, and you will see that gases are generally speaking more disordered than liquid. Liquid still tends to have some order. But another way of thinking about liquid and gas in a general sense is gas tends to have lower density than liquid, right? Gas tends to have higher volume than liquid, right? That's why I said that this part over here is gas and this part over here is liquid. It's just two phases. Think about it in that way, right? One is a lower density phase and one is a higher density phase. That's the idea over here. Okay?
Pressure volume diagrams, are these also phases?
Yeah.
So how do we see?
Well, no. This is an extensive quantity. Kind of.
So it's not.
If it's molar volume, you can think about it that way.
So then how would we see transition? Like in the PT diagrams, we have these like boundaries and we have.
Yeah, so because both are intense. Here, yeah, so we will see transitions now. So, but here, so let me just write down. So in the PT, in the PT diagram, what was the region of coexistence between liquid and vapor? Let me call it liquid and gas, so it's consistent with later. It was a point, right? And it looked like a line. So as you change at any given temperature, there was one point, one pressure at which liquid and vapor coexisted, right? Liquid and gas coexisted. Here, all of this is the liquid plus gas coexistence region. So it's different. It's not a phase diagram because this is an extensive quantity. So you have to be careful. Gibbs phase rule won't just apply. You could write down an equivalent Gibbs phase rule here, but you'll have to be careful in how you derive it. So you have a gas on the right. Yeah, right.
have multiple possible volumes for the same question, then does that mean an MPT don't uniquely determine the state?
If you repeat again, if you have multiple,
This is an isotherm, these are all isotherms.
this is an isotherm, yes.
Fixed temperature.
Yes, at a fixed temperature, you have,
At a given pressure, you have multiple possible volumes.
yes,
So that means MPT cannot uniquely determine the state.
number is always constant, so don't worry about that. So pressure and temperature cannot uniquely determine the state. You have to have the volume also. So at the same pressure and temperature, your system could be at different volumes.
So
Because you have two phases, that's what you have to be careful. It's not a one-phase system.
they
You
are
have two
coexistent.
phases.
That's why it's the coexistence.
It's a coexistence area. Yeah, it's a coexistence line here. Okay, so it's two phases. So, okay. Any more questions? I'm gonna build up slowly. This is slightly abstract. So we will always use van der Waals as an inspiration, and keeping in mind that the weird behavior in the middle will fall out. Okay, we will have a straight line like this in the middle. So let's redraw this curve once again. And this time, what we are going to do is to draw a whole bunch of van der Waals. Okay, so we have pressure and temperature at not pressure and temperature. What are we doing? Pressure and volume. And all of these are isotherms. So we have pressure and volume at very high temperature. We have something that looks like an ideal gas, PV is equal to nRT. Okay. As we go to very low temperature, it looks in the van der Waals picture something like what am I doing? Sorry. Something like this. Okay. What happens? So this is very high T, and this is some low T. What happens in intermediate temperatures? You have to go from the bottom curve towards the upper curve, right? And you can sketch it in MATLAB, Mathematica, or Python, wherever you want, and you will see that as you increase the temperature, it starts to look like this. Just similar shape, but it starts to approach the ideal gas law. So this is increasing temperature. And notice how I got the liquid gas coexistence region for any given temperature. For any given temperature, how did I get the liquid gas coexistence region? I looked at the van der Waals curve, right, over here, and I looked at the three solutions it has, right? And it corresponded to the area between the first solution and the right solution. It's a bit of error over here, but we can ignore that. Okay, so this is what it corresponded to. So over here also, we take a pressure and we look at the three solutions it's going to have. One over here, one over here, one over here. Okay. So at any given pressure, we are going to look at the three particular volumes that might exist. So as we keep increasing the temperature, what's going to happen to this blue point? Will it move to the left or will it move to the right? Does everyone agree with that? Right, so this blue point will move to the right. What will happen to the second blue point? It will move to the left, right? We really don't care about the second blue point. What matters is the end one, right? Over here, look at this. We just said this was an artifact of the van der Waals gas, right? This is all liquid gas. So the second blue point just doesn't matter. What matters is the third one. The third one is also moving to the right. So for this second curve, you can see it's going to be somewhere over here. For the first curve, it's going to be somewhere over here. And then it will keep moving up. So and we are not going to worry about the middle one. So now you can join these curves, these dots, and you get something that looks like I should really not have stretched that one that far out. Something like this. So you get a dome, okay? From the left side, you have curves moving to the left, points moving to the left. From the right side, you have points moving to the, no, from the left. These points, the left points are moving to the right points are moving to the left. And to the left of this curve, all of this is liquid. To the right of this curve, all of this is volume, right? Sorry, vapor. So oh, I should not use V. Let's call it gas. G. So this one keeps moving to the left. This one keeps moving to the right. This one keeps moving to the left until they coincide, right? And then you get to a certain point. What is in the middle? In the middle, you have liquid plus gas coexisting together. This particular point where they meet is the critical point. This particular pressure and this particular temperature, this is PC and this is TC. This is critical point.
Excuse me.
Yeah.
Is it perfect dome shape or it is like towards more tilted towards left side?
That depends on the chemical of interest. So I don't see any reason why it would be symmetric. For example, it could be tilted left, it could be tilted right. I don't know, depends on the particular chemical, right? So carbon monoxide has a critical point, water has a critical point, they will look completely different. Yeah. So we can, the reason why van der Waals equation of state is useful, even though we are not using it, is because we can use the van der Waals equation of state to actually calculate the value of the critical pressure and the critical temperature, okay? So why did we get these three solutions? Even though we ignored the middle one, why did we get this point and this point? Because it was a cubic equation, right? And in this cubic equation, you have a change in curvature. As you keep going up and up, look what's happening. This is becoming flatter and flatter. And finally, there is no change of curvature, right? What is the slope of the ideal gas form? It's always negative, right? And over here, you have negative slope and you have positive slope, right? So the curvature change. So this point can be characterized as follows. This is, and I will write on the next page. So critical point is a point at which the partial derivative of pressure with respect to volume at constant temperature becomes 0, and the second derivative of pressure with respect to volume also becomes 0. Okay? And again, let me draw that thing again at this page so you can stare at it. So and we took this point 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 and we joined something like this, right? So, sorry about that. So this particular point is characterized by these two equations. Is that clear to everyone? All right. Repeat that.
So you, like the whole argument comes from the fact that like it's a good equation, right? You have
Yeah.
multiple solutions.
Yeah. Yeah.
So that like in
that in fact, if you had only one volume, if you had an equation of state which permits only one volume at a given pressure and a given temperature, you won't have different phases.
Okay,
It won't happen.
okay, so that's why we.
Yeah, it doesn't have to be just ideal gas law, right? PV is equal to nRT, but we could have changed this to, I don't know, PV square is equal to N R square T, right? And let R take care of dimensions. Even that would not allow this to happen, right? So you need to have such multiplicity. Yeah, go ahead.
So critical point, like not always the maxima of that Carnot set. If it's a maxima, then double derivative must be less than 0.
No, it's an inflection point. It's more than a maxima. It's an inflection point. It's the point at which the maximum changes from to minima, right? It's an inflection point. So this is an inflection point. So we can. So what do we need to calculate? We need to calculate the value of the critical pressure, the value of the critical temperature, and the value of the critical volume, right? We see, because this happened to a curve at a particular temperature, right? This did not happen at all curves. These are isotherms, right? So this corresponds to isotherm at a particular temperature. So we need to calculate three things. And we have two equations. How do we do that? Can we get three things from two equations? Do we have only two equations? We also have the equation of state, right? So we have three equations. We have equation 1 is P is equal to nRT by V minus NB minus A N square by V square. Equation 2, partial P by partial V at constant T is equal to 0. Equation 3, partial square P by partial V square at constant temperature is equal to 0. So three equations and three variables. When you solve all three together, you will get the critical volume is equal to 3B. The critical pressure is equal to A by 27B square. And the critical temperature is equal to 8A by 27BR. The internet is full of this solution. You can go and find it. It's just algebra. Go ahead.
I still don't really see how we can have a critical point and a point of inflection at the same point.
So all of these are point of inflection, right?
I see that, yeah.
That's what I'm saying. It's where the point of inflection stops being a point of inflection. So I should be more careful. This is where the inflection point disappears. How about that? Right? Until this temperature, you actually have an inflection point. What is an inflection point? Inflection point is at which the slope changes, right? At this point, at this temperature, there is no longer an inflection point, right? So it's the point of disappearance of the inflection.
Inflection points on the contact changes, right?
Yeah.
Okay,
And
so
now it's just, what is it, concave or convex, whatever, you know, it's just one behavior. So, okay,
how do we
let's
know the second derivative is 0 at that point?
it is the, so this, how do you define an inflection point?
So the concavity changes from.
Mathematically, tell me an equation. F is equal to f of x.
Okay, second derivative of f at x is less than on one side versus the other side goes negative.
So you are invoking third derivatives.
Yes.
Okay.
Before
Mhm.
fundamental with regards to the discussion. So we have this isotherm,
Mhm.
and the way we chose the 3 points was by choosing an arbitrary pressure and then drawing
At any pressure.
at any.
Yeah, at any pressure, this is going to happen.
No, so because the way we drew this connected graph was that we had an isotherm at a higher temperature,
Yeah.
and then again choose a different pressure.
Yeah.
So how do we choose a different pressure? Is there any?
That's the control parameter. At any pressure, you take any pressure. You want high pressure, you go here. You want low pressure, you go here.
Because for let's take the first isotherm.
Uh-huh.
If we choose a very high pressure, then it will not pass through 3 points.
Which this one.
Yeah, this one. If we choose a very high pressure, it will because it has a maximum.
Sure, that's fine. That doesn't bother us.
So my question is, so since we have different isotopes at different temperatures, shouldn't there be some restrictions on how we choose the pressure? Otherwise, when you join all these points together for it to form a nice point.
This is why this point, zero curvature, comes into play. It has to be the pressure through which you are passing through this point. This point, the point at which double derivative is zero.
Yeah.
Okay, so that is, so why did I pick, so you are saying, why did you pick this pressure? Why did you not pick this pressure for this cycle?
And more importantly, for the next point, you chose a point that is slightly higher. If I chose the
The reason I picked a slightly higher point is because this point has now moved up.
oh, you want it to be vertical. Okay.
It might not be vertical, it might not be vertical, but it will move up.
Okay.
It looks vertical in my terrible drawing, but it might, it's what we know is the point at which double derivative is going to be zero. That's going to keep moving up. Right?
Okay.
And if we go back, what I was about to scroll on this side idea. If we look about real materials, the thing that connects van der Waals to real material is that this is preserved. Right? So the van der Waals had this behavior, which is spurious, and the real material, the black line, crosses through that central point. Okay, so in order to calculate where will the critical temperature lie, the critical pressure lie, we need to have the double derivative zero, the first derivative zero, and it should lie on the equation of state. So that's why we have three equations. Okay, and maybe my usage of inflection point is confusing you. Okay, so don't worry. I think it's correct, but don't worry.
Can I ask one question?
Yeah, please.
So if it's not an inflection point anymore, then I'm back on Ben here. But so if it's not an inflection point, then the second derivative isn't zero, right?
Oh, you guys will not leave me from inflection point.
Yeah, the second.
In
Because isn't that the definition of an inflection point is the second derivative is zero?
sure, well, yeah. So okay, so Ben was tripping me. That is the middle point. Inflection point is the point F. Okay. An inflection point of the curve is where F double prime is equal to zero.
Right. But
Okay.
that's the whole point of what we're saying is that it's not an inflection point anymore.
No, I never said it's not an inflection point. I just told Ben, don't worry about
But
it.
where inflection point disappears. That's what that says.
Here you have an inflection point,
Yes.
right? Here you have an inflection point.
Yeah.
Do you have an inflection point in the ideal gas law?
No.
That's what I meant by disappears.
So how can we say that the second derivative is zero?
Yeah, yes.
That is the last temperature at which you can get second derivative equal to zero. Beyond this temperature, the second derivative cannot be zero. So you're saying exactly what I'm saying.
Okay.
Beyond this temperature, you cannot have second derivative.
You mean beyond this,
Okay.
the,
Yeah,
beyond this.
great, good,
Got it.
good. No, I really appreciate this.
Graham, I still don't get your answer.
Oh.
Because like you're saying that, oh, we know this like vertical line or something like that. But then like you're using this peak to like discover where the inflection point is. Like I get if you want to solve for like the PV and T of the critical point by using like the three equations.
Yeah, so why did we
I
get to
don't
those?
get how you build it.
Yeah, how did we get to those three equations? So why did we build it that way? For that, we have to remember this real curve, right?
I don't know, why did you pick the pressures?
That's exactly what I'm saying. This is the pressure at which you cross through the inflection point. That's special about this pressure, right? You could have taken this pressure. Forget about van der Waals gas for just a moment. Think about the real material equation of state, okay? The real material equation of state looks like this. So if you didn't have van der Waals, is the choice of pressure then not obvious?
Yeah.
It's obvious, right? So for a real material, which pressure to take is obvious, right? You just see a flat region in liquid plus gas. For a van der Waals, that flat region happens to cross through the
So
inflection
for
point.
every isotherm, the pressure you pick
Is the one crossing through the inflection point.
yeah, corresponding to like that real version
Yeah.
at the same, okay.
The
How
real
complicated.
gas, not gas, the real chemical will go through
Yeah,
the
yeah.
inflection point. So that's why you need to pick the inflection point. And again, I was going to scroll this, terrible. So this is the temperature at which inflection point disappears, not the pressure or volume at which inflection point disappears, the temperature at which it disappears. Okay, good. Yeah.
The pressures that you pick, I could draw like corresponding real isotherms through them, and then that's like
Yeah.
flat region.
Yeah.
That's why.
Exactly. And real things exist as such a flat region. Okay. Yeah, so I'm very glad that you asked this because I know for a fact when I taught 481, when I substituted for a professor, and they said, "Oh, it's just critical temperature tomorrow. Just go and teach it." I was like, "Wait, what? This stuff is really complicated. It is complicated. And the more you think about it, when you do StatMech, it will come back and bite you even more. There has been at least one Nobel Prize for critical points, for critical transitions, and how to study them, and there will probably be more. Okay. Everyone more or less happy with it? Ben happy? Lydia happy? Anjali happy? Dosia, are you happy? In a broad sense, who is happy? No one is happy if you think about it. Okay. So, how would this work for a real chemical? If you have measured the equation of state, you can go through this procedure again, right? The algebra will look a bit more complicated. You will probably have to do it numerically, but it's the same three equations, right? Equation of state, first derivative equal to 0, second derivative equal to 0. Solve for it, you get the critical point. Oh, yeah.
Could it be volume 3 NB or 3B?
Well, that depends on whether it's molar or not.
I'm just looking at the dimensions.
Again, molar.
Molar volume.
Molar volume is 3B per mole. Okay. What we are going to do next. So this is the last I wanted to talk about critical point. It's almost like an isolated picture, but it kind of completes the picture. You understand most things in a water phase diagram now, right? You understand why is the slope negative. You understand why it should be flat or steep. That depends on the Clapeyron equation, to which the Clausius-Clapeyron equation is an example. And hopefully you have a better understanding of why does the boundary just stop in the middle at a particular temperature. Okay, and I recommend you go and look up like YouTube videos or things like that for critical behavior. You will see it's really crazy. It's like it's like you're boiling water, but bubbles are not appearing, but the whole vessel, all of a sudden, the whole thing is a bubble. That's crazy, right? That's what's really going on. And you think, oh wow, the whole thing is a bubble, but the next moment, the whole thing is water. It's very, very crazy, and it matters a lot. It's one of those things. Critical behavior has existed for 100 years or more, like before atomic picture of things, and it still matters a lot because people use this to model variety of things. In my group, we study neural networks, right? And you're training a neural network, and you can see critical behavior in training a neural network. All of a sudden, the neural network parameters change from one set to another set, right? So people use, or sometimes small changes have to happen. People use this to model elections, right? I vote Republican. No, I don't vote. I have green card. But let's example, person A votes Republican and person B votes Democrat, right? And changes are happening that you have having small bubbles of Republicans happening or small bubbles of Democrat happening. But then something happens and the whole state changes from Republican to Democrat, right? So people use these things to model things like that also, to model elections and all sorts of things. Because here we are studying phase changes in chemicals, but phase changes can happen in a very, very general setup, be it neural networks, be it society, whatever you want to model. Okay. What we are going to do, so we started with thermodynamics from a very abstract perspective, right? We started with our Callan postulate and everything, and that's still our guiding force, right? Why is it our guiding force? Because G, right? We are working with G at constant temperature and pressure, and we know that everything happens in the direction of reduced G at constant temperature and pressure, which is a direct restatement of Callan's postulate, right? If you did not have constant temperature and pressure, if you had constant number, volume, and energy, then it would be increasing S, right? So what we are doing now is to take all of this and make it more practical. And in order to make it more practical, we really need to think about, even though water is nice, we need to think about multi-component system, right? We need to think about things where it is not just one species, but you have many species existing together. This part will have some easy algebra, but the equations that you get here are actually very interesting. At least I like this part a lot. Hopefully you will also like it. So now we are going to talk about mixtures of different components. And here the taxonomy is going to be as follows. We are going to talk about ideal mixture. Then we will talk about something known as regular mixture. And finally, there is a real mixture. I won't talk about real mixture as much, but I will spend time talking about these two. And you will see why they are quite powerful already. So for an ideal mixture, let's consider Na moles of A and Nb moles of B. Okay. And let's say we have a container. In this container, we have a partition. On the left side, we have A. I'm making it look like red. On the right side, we have B. We are making it look like blue. So you have on the left side Na moles of A existing at a temperature T and pressure P. And on the blue side, you have Nb moles of B existing at the same temperature and same pressure P, but in the middle you have a partition, right? So the red has to stay on the red side and the blue has to stay on the blue side, on the right side. And let's assume for now, for the ideal mixture part, that A, B, both are ideal gases. Okay, so this we are going to call initial or I. And now we are going to remove this partition. Okay, no partition. And this we are going to call as final. Assuming they are ideal gases and the temperature and pressure are still kept as T and P, right? That doesn't change it. So you were already at thermal equilibrium, you're already at mechanical equilibrium. You did not have chemical equilibrium, right? You let chemical equilibrium happen now. How should it look like? Where will red go? Where will blue go? Huh? It will mix. It will be completely uniform, right? For ideal. If it was not ideal, it won't be true. Can you think of cases where they might not mix even after removing the partition, they stay the way they are?
Oil.
Huh?
Oil and water.
Oil and water, right? So for example, oil and water doesn't do that, right? So this is krypton on xenon type example, right? You have krypton on the left and xenon on the right. But we will get to oil water type situation just building from this math, which is really interesting. So now the red will be all over. And the blue will be all over. So we are talking about a process at constant temperature and pressure. So if we want to talk about the direction of spontaneous change, we have to use Gibbs energy, right? To talk about this because it's constant temperature and pressure. So if you started from the top one, you will go to final, right? The final is the more spontaneous state to happen. So which one should have lower Gibbs free energy, GI or GF? Huh? Go ahead. No, but this was a mental partition, right? So I'm saying that all biophysics students are sitting left side, all biophysics students, chemical physics students are sitting right side, and there's a mental partition. As I remove this mental partition, equilibrium will establish, right? And you will have mixture. And this mixture state, you cannot go back to a sudden, unless there is some driving force the biophysics students do not like the chemical physics students, unless there's something else going on, then it's not ideal anymore, right? That's oil and water situation. If it's ideal, you cannot go from the final to initial. There is a sense of finality here, right? You will stay in the second one. So GI must be more than GF, right? For this to happen. That's all fine. Let's try to write down expressions for GI and GF. How do we do that? And that's where you have to think a little bit more. So far it's obvious, but now we have to think and use some of the equations we did in the last few classes.
That is like
Fugacity? Similar equation. So yeah, help me. I got Maria Delia's attention. And I follow you on Twitter now, so I have got you. I saw, yeah. I saw you were already following me. That's because of Pakoda. I have more followers than Daryl Pines. Let's say something, right? Actually, I'm not that active. My posts are very targeted. If you go and look, so there is something known as the, do you guys know who is Kim Kardashian? Do you know the Kardashian index? The Kardashian index is the ratio of your H index, which is the number of times of citations, something like that, of your papers, divided by your Twitter number of followers. So my H index is actually reasonable. My Kardashian index is not that high. So just to defend myself. But my posts are meaningful. They involve dog. Yeah, well, it is what it is. I don't even have the app. So GI, before we use the equation Maria that I said, and we don't need to use fugacity because it's ideal, right? So we'll be able to get away with pressure. Fugacity was introduced to mimic pressure, right? So here we use the same equation, but initial GI comes from A moles of N moles of A multiplied by chemical potential of A, right? Plus NB mu B. This equation should, every time I write this equation, I'm sure some of you would be like, I don't quite understand where that equation came from. But remember when we talked about G, we said that G is equal to mu I Ni, right? G had a special connection with mu I. A was not equal to mu I Ni, right? Gibbs Duhem followed from this, but this didn't have a name. We can call it Maria Delia equation. Did I get your spelling correct? Yes. Okay, good. So GI is equal to Na mu A plus NB mu B. That doesn't quite help us. Now we will use the equation which led us to the fugacity type equation. Okay, let me write this one on the next page. So this was page 4. So GI is equal to Na mu A plus NB mu B. So that's going to be Na multiplied by mu A can be written as mu A naught plus RT ln P by P naught, right? And NB mu B naught plus RT ln P by P naught. And again, if this step of going from mu A to mu A naught plus RT ln P by P naught is not obvious to you, please go home after class. Don't go home now. Go home after class and derive. This will play a lot of role in what's coming next. Okay, so this equation should be second nature to you. How did we get this equation? Just to recap, we used the fundamental equation for dg, right? dg minus vdp plus dg is equal to vdp minus sdt plus mu dn, right? And then we thought about constant chemical same number of n, right? We looked at this equation, we put in Murray's equation, ideal gas law, right? We integrated, and that's how we got G is equal to G naught plus RC ln P. And then we said if it's a one component system, then G is equal to mu n, right? That's how we got it. So this derivation, please go home and check. Yeah. T is constant. Everything is constant temperature in this case, okay? So set P naught for both of them equal to 1 bar, okay? Why do we do 1 bar? Then ln P by P naught can just be written as ln P, okay? That becomes nice. So GI becomes Na mu A naught plus RT ln P plus NB mu B naught plus RT ln P. Okay, I didn't number equations today. Let's call this equation number 1. Do I have a 1? I don't think I do. Yeah, so this is 1. So this is equation number 1. That's GI, okay? The initial Gibbs energy, when you had a partition, things were not mixed. A was acting independently of B and vice versa. Now we have to think about GF. How do I write GF? What do I need to change in equation 1 to write GF, which is after mixing? Which potential? Chemical potential? So if in loss just starts from the basic equation, right? G is still is equal to summation mu I and I, right? No one is going to challenge that. Whether it's mixed or not doesn't matter. So G is still going to be, and Na is still the same. That has not changed. So it's this mu A which is now different, right? If mu A was the same as mu I, then well, then there is no mixing. The free energy initial and final is same. You will just naturally go from A to B and it won't matter. So this is going to be Na mu A F plus Nb mu B F. And this mu A F will still follow the same equation, but with one crucial difference. You will now have mu A naught plus RT ln partial pressure of A. Okay? Plus NB mu B naught RT ln partial pressure of B. Okay? Let's take a moment to stare over this. I'm not saying anything about yet what is the connection between partial pressure and the total pressure. For an ideal gas, the partial pressure becomes mole fraction multiplied by the total pressure. That's one of those laws we study. That is like one of those things that makes you hate chemistry as a high school student, because everything has a name, right? It's like Henry's law, Dowd's law. Does anyone remember this? For an ideal gas, the partial pressure is equal to mole fraction multiplied by the pressure. It's got a law. See, no one remembers. Good. I'm happy that no one remembers it. It's got some name. And you're like, wait, why does it have a name? Kind of pointless. But for now, it's almost like a fugacity type statement. It is what would lead to this equation being true. That's how the partial pressure is defined. Think of it that way. So I'm going to call this equation 2, and these are partial pressures of A.
Right, that's the sum of the partial pressures of total pressure.
Yeah, that's all I have said. That is always true, right? Sum of partial pressures is always total pressure. But whether the partial pressure is mole fraction multiplied by total pressure, that's not guaranteed. That has to be ideal behavior. For ideal gas, PA is equal to Na by Na plus Nb multiplied by P. Pb is equal to Nb by Na plus Nb multiplied by P. Na by Na plus Nb has a name. It's the mole fraction, right? It's the mole fraction of A. So this can also be written as Xa multiplied by P. And this can be written as Xb multiplied by P. Okay. So any questions about this? So let's put equation 3 in 2. Again, so I will write down everything again. So Gi was Na mu A naught plus RT ln P plus Nb mu B naught plus RT ln P. Okay, and Gf is Na mu A naught, and remember mu A naught is the same because that's just the reference chemical potential. That does not change between initial and final. That's just a reference value. So this is same, the mu A naught part. And RT ln PA plus NB mu B naught plus RT ln PB. And again, mu A naught and mu B naught, they don't depend on whether you have initial or final. And at this point, we invoke the ideal gas law, the ideal behavior, and say PA is equal to XA multiplied by P. and PB is equal to XB multiplied by P. And we are assuming ideal anyway because we are not using fugacity, right? So it's all good. So this becomes NA. This was equation 1. This was equation 2, and we put 3 into GF becomes NA mu A naught plus RT ln XAP plus NB mu B naught plus RT ln XBP. That's called as equation number 4. So now we can calculate GI minus GF, right? And we expect GI minus GF to be positive. We expect the final state to have lower Gibbs free energy. Let's see that if that's actually true. Jacques, you speak French, right? Oui, merci beaucoup. So now this is the class where I make my favorite, most terrible French joke. It's going to follow soon. Wait for it. It involves calculus and French. Now you're intrigued. Don't guess. It will happen. It's stupider than you can imagine. So let's do actually I'm going to do GF minus GI, so I don't confuse from my notes. So we want to do, sorry about that. So GF minus GI. So what's that going to be? Yeah, let's write down everything explicitly. So that is NA mu A naught plus NA RT ln XAP plus NB mu B naught plus NB RT ln XBP. That's GF, right? And subtract out GI. That's going to be minus NA mu A naught minus NA RT ln P minus NB mu B naught minus NB RT ln P. So few things cancel out. NA mu A naught cancels out. NB mu B naught cancels out, right? And we have NART. This has NART, low battery. Oh, and this also has NART. Okay. While this one has NBRT and this one also has NBRT. Okay. So let's combine these term by term. What do we get? We get NART ln XAP divided by P, right? Log of A minus log of B is equal to log of A divided by B, right? And A is XAP and B is P. So P cancels out. What are we left with? NART ln XA. No, where have I missed XA? No, I don't think so. Plus NBRT ln XB, right? So this is GF minus GI for the full system, right? Now we think about GF minus GI per mole. How do we do that? We divide by Na plus Nb, right? So per mole, GF minus GI is going to be Na divided by Na plus Nb RT ln XA plus Nb divided by Na plus Nb RT ln XP. And Na by Na plus Nb has a name, that is XA. And Nb by Na plus Nb has a name, that is XB, right? So, wait just a moment. Everyone okay? Can I move? So, this GF minus GI also has a name. It is known as the delta mixing of Gibbs free energy. Okay, it's the Gibbs free energy difference due to mixing. Per mole is equal to XA ln XA plus XB ln XB. For a two-component system, we don't need to use both XA and XB. Why not? Because XA is 1 minus XB, right? What's the point in carrying both of them? Next time we will talk about multi-component, but for two-component, let's just call XA equal to X then xb is equal to 1 minus x, okay? So what do we get then? We get that, oh, I also here I missed an RT, that's super important. So what do I get? I get delta mixing G divided by RT is equal to x ln x plus 1 minus x ln 1 minus x. And that we get this equation is like ultimate thing. I really, it makes me happy. Has anyone else seen such x ln x plus 1 minus x log 1 minus x equations elsewhere, far outside chemistry? Where? Far outside chemistry, like very far. This is nothing but Shannon entropy. Shannon was the reason we have computer and internet and anything else, right? Shannon was this incredible scientist in the 1950s who basically wrote down 3 or 4 papers, just go and read them if you have time, where he talked about what is the entropy of information. And Shannon entropy also looks like this. It doesn't have X, it has probability. It looks like P log P. This is, and I don't think Shannon was inspired by thermodynamics, or maybe he was, but who knows. I find this fascinating. That's the equation shows up. So, okay. So we got x log x plus 1 minus x log 1 minus x, and I haven't yet I have to make, we need to plot it and to see that whether it is actually, we want it to be positive or negative. We want final Gibbs free energy to be lower than the initial free energy, right? So we want this thing to be negative. Is it negative? If you put x is equal to 0.5, what is going to be the value? It's going to be 0.5 multiplied by log of 0.5. That's a negative number, right? Plus again, 0.5 multiplied by log of 0.5. It's a negative number. So in the middle, it's clearly negative. In fact, you can see for any x, 0 less than x less than 1, ln of x is negative, right? And x is positive, right? X is positive, ln of 1 minus x is negative, and 1 minus x is also positive, right? Because we have defined the range this way. So both of these terms are negative for any value of x. The curve will always be negative. And I will resume from this. I like this curve so much that I will resume from this one next point, next class. So we know it's going to be negative, but there is something which is very interesting here is, so it starts, so what am I drawing? This is G, and this is X, and this is X is equal to 0, and this is X is equal to 1. So we know it's always going to be negative. My question for you is, what is the slope of this curve at either end? How quickly does it become negative? So if I set X, or even simpler question, if X is equal to 1, then what is this curve? Are you sure? Be careful. If X is equal to 1, this curve part is 0, 1 log 1. How about this one? Why?
1 minus x.
Or other, let's think simpler. What happens to this as x tends to 0? Why? Can you prove that? Here comes my French joke. You can prove it using what is known as the L'Hospital rule. Correct pronunciation?
Sure.
L'Hôpital, right? How do you pronounce it correctly? L'Hôpital. I mean, so beautiful. Not you, your pronunciation.
You also spelled it wrong. You know what?
Really?
There's a circumflex on the O in the last.
Oh, I'm not gonna write those. I have to put like
But it's fine.
little hat on the O, and
Because the hat represents the S that tragically got lost in the photography.
let's just call it L Hospital. Okay? L Hospital. L Hospital. Okay, 5% battery left. We're getting there. So that tells you that if you have a function where you have log of 0, you can take the derivative of that thing and get that thing, right? So next time what I will show you is that you can also use this to calculate that it looks like this. it goes to zero at both ends. It's always negative, but it falls down with a slope of minus infinity. So this slope is minus infinity, and this slope is plus infinity. And you can see it's always negative. So this is, what did we show here? We showed the free energy of mixing of two ideal gases. Okay. Next time I will go through this curve again. And so go practice your L hospital and make sure you see it. I'm not going to do the math. Just go at home and see that. If you want, I can do it. The amazing thing about this curve is, first of all, the most amazing thing is the x log x formula, which I really like. You know, for information theory and thermodynamics have similar formula. Secondly, this behavior that at the ends, the curve has this slope of minus infinity and plus infinity, that is true for everything. It doesn't have to be ideal. It doesn't even have to be classical. It could be quantum mechanical. If it's at equilibrium and you're mixing things, the slopes have to be minus infinity. And that's really important. That tells us that it's very, very hard to create a pure material. Adding impurity, anytime you add an impurity to something, the free energy drops down infinitely, right? It really, really shoots down. That is the reason why nanofabrication of, like, you know, you have, when you have these, who here, a lot of you do experiments, right? What are those rooms called where people have these masks and they are working on things? Clean room, right? In clean room, you have to be extremely, extremely careful not to have any impurity. If you're trying to make anything which is pure, the slightest impurity would like to go and sit in it for this reason, that the free energy, you know that spontaneous direction is where free energy lowers down, right? And this curve is showing you that at least for ideal behavior, the tiniest amount of impurity lowers the free energy infinitely, like by a huge slope. It's tremendous. And the curve in the middle, that's true only for ideal behavior, but this ending behavior is true in general. Okay, so next time we will start with this curve and we will take over from here. So before Thanksgiving, you will have one class, which there won't be any class. So at least you have some time. We had a very contested, controversial election, but democracy won. There were lots of campaigning on both sides, but you know, it is what it is. And democracy won with an absolute majority. So the side that lost should not complain. It was a 2/3 majority. Okay, so there will be one class when there won't be any class. So you have at least guaranteed some time to work on the midterm. And one class before Thanksgiving will be on Zoom. I don't like teaching on Zoom, but you know, I have some limitations, so I have to do that. And I don't think we will need an extra class. I think we are doing okay on pace. We are covering what I wanted to cover. You know, it's one of those things where I don't want to teach you too many things. Although some of you might think I've taught you too many things, but when I get the course evaluation for this class, it's always bimodal. Some students think I taught way too much, and some students think I did not teach too much. You know, and I have to traverse that curious line. So, any questions? Okay, so see you on Thursday.
So if that's true for all materials, then how are any pure materials stable?
Let's get to that later. Next class.